Hey guys, it's Joe here, and I'm back for my second video on how to add voltages and currents. Now this is important when doing your applications, but let me go ahead and explain why. Now before addressing addition of currents and voltages and how that works, I need to discuss what series versus parallel is. Now series is when you have a node, and we can call that node anything. We'll just call it A, which we can see right here on the left hand side. Oh, pardon me. So we have node A, and then we have node B, C, and D. And what I'll define as a node is just this point, this point, this point, and this point. Now, as you can see, A touches B, which B touches C, which C touches D, and all of them have a commonality of A through D. Now, they do not split off. As you can see on the right section, if we were to call this one A here, this is all of node A. And say we call this one B, this is all node B. So since A and B are shared between all three of these squares, so the square could be a resistor, it could be a current source, they are considered to be in parallel, as opposed to these do not share each one. They have a sequential letter after, which they still share A, starting at A, and they go through D, and they do share B and C in between, so therefore they're in series. And these other nodes, there's only two nodes, A and B. And A and B, all of these resistors or all these squares share the same nodes, therefore they are in parallel. Now this resistor here is also considered in parallel with everything to the right of here, because if you were to have A, and we can call this a new node, maybe after everything is done, we could call it C, but technically these would be in series afterwards if they shared the same node. Sorry if that's a little confusing, but we will do some analysis which will clear that up later. Now the next thing I'm going to go over is adding in series and adding in parallel. Now voltages do not add in parallel, and currents do not add in series. That wouldn't really make much sense, but I'll get into it here in a second with my explanation that I went over with you in the introduction, which was a river. Now voltages do add in series, as I can give you an example here. We start off with our ground. This is a symbol for ground, the little triangle. Another one is this one here, which is a triangle, or this guy right here, which is ground. Now basically they add, so if you take 5 plus 5 plus 10, you're going to get a grand total of 20 volts. The same in currents is if you have currents in parallel, you have 1 amp plus 2 amps is 3 amps, and 3 amps plus 3 amps is 6 amps. So your grand total is 6 amps. Now with current, this would make sense, and I will show you why this makes sense here on the next slide. Now as you can tell, I gave you an example of a river, and this is my best example of a river, this drawing right here. Basically it is a 1 foot deep by 1 foot wide river. Now it starts off at this point right here. Now you have one river that's 1 foot by 1 foot, and there's a certain amount of water that's flowing through it. Let's say that we have the river splits into this little shape here, a little square. One goes this direction and the other goes that direction. Now let's say that this right here is 1/2 of a foot wide, and it's still 1 foot deep, and this is 1/2 of a foot wide. Now, as you would expect, the water, all of the water is going to flow through, we'll call this one A, and we'll call this B. So through part A, half of the water is going to flow through A, and half of the water is going to flow through B. Now that's just arbitrary half and half. Obviously if I made A 3/4, that means 3/4 of the water will flow through A, while only 1/4 of the water will flow through B. Now how this makes sense to me, and like I was telling you before, is if you have something in series, and let's say we have water going in this direction, and it's a total amount of water is 1 amp. Now if you have a resistor in series with another resistor, regardless of how wide the river is or how narrow the river is, the same amount of water of 1 amp is going to flow through this whole entire stream or branch. It doesn't matter that the resistors are different values at all. All that matters is the water that you input into it in series is always going to flow through it over time. Now, like I said, the resistance of the water can restrict the amount of time it takes the water from going from point A to point B, and speed is a resultant of that, which is analogous for voltage. So there may be a voltage drop across the resistors, meaning the speed could be faster or slower. However, the same amount of water is going to flow through that water in, the channels in series. However, with parallel, with the original drawing I showed you here, the water is 1 amp, and half of the water is flowing here, and half of the water is flowing there. Now, basically, if this water then joined together with each other at some sort of junction, let's say that we can call it ground, so let's say that this is ground here, and we'll say that this point is ground here, and we'll just say these grounds are the same node. We'll call it node C. So basically A and B join together at C. As you can tell right here, here's point C. The water is going to come here, the water is going to flow down here. Basically, half of the water plus half of the water is all of the water. So for example, if this were 1 amp here, this would be half of an amp at part A would flow and half of an amp at part B. But at part C, the half amp of water and the other half amp of water is going to join each other again, which creates a full amp. So your output would be 1 amp. So 1 amp is going in, now 1 amp is going out. Now this is a good introduction to Kirchhoff's laws, which would be a Kirchhoff current law and a Kirchhoff voltage law, meaning that if you start at one point here, we'll start at the beginning, if it gives you 1 amp, the sum of the water, so for example if we have 1 amp flowing through here, part A, it's going to, in part B it'll split, so half of an amp. So basically what that means is 1/2 of an amp plus 1/2 of an amp should equal 1 amp, and in our case it does. So next video I'll go over Kirchhoff's current and voltage laws. Maybe go ahead and redefine some of the definitions that I gave you guys that may not have been as proper, and hopefully I can explain this a little better to you. Thank you. Bye-bye.